everyone. Let me introduce myself. My name is Mittu Walia. I'm working as a research associate at ADIW01. Right now we are working on analytical solutions of nonlinear PDEs. My PhD work is on nanofluid flow. Using the numerical discretization to solve the fluid problems, we have used finite difference, finite element method, and some of the numerical techniques like spectral analysis method. But in this position, I'm working on this analytical study. Analytical study, or I can say the semi-analytical methods to solve the fluid flow problems. So this project is actually funded by the SIR. And okay, so yes, so this conference is all about the how the structure formation in the oceans, atmosphere, active fluids, reactive fluids, or any kind of plasmas. So any kind of fluid flow we can describe by using the nonlinear PDEs. And to handle any kind of nonlinear PDEs, we generally use numerical methods. Now, numerical methods, there are two difficulties, or it somehow kind of tedious work to handle the convergence analysis or stability process. So, the difficulties in the numerical methods, basically we'll have to deal with the stability or convergence analysis or the round of errors. Every fluid flow, whether it's gas or we can say fluid, we can describe by using the nonlinear PDEs subjected to any kind of initial conditions or boundary conditions. So motivation of our present study, it comes with the fluid flow but using the analytical approach. Here we are going to discuss the Pavlov equation. So Pavlov equation is actually the generalization of DKP equation. Again, it defines the commuting flows. Pavlov equation, it gives it is actually class of hydrodynamical flows, or we can say commutative flows, where we have dispersionless flows. Now, here this Pavlov equation, we are just having a nonlinear PD without any conditions, irrespective of initial or boundary condition, to solve this fluid flow, which is dispersionless commutating flows. Now we can solve, we have like this equation, we have solution using the numerical discretization, that is finite difference method. But again, the finite difference method, we are just getting the approximate solution. Here we are using HM method, which is semi-analytical approach to solve this nonlinear PD. Now what we do to apply this HM method, we introduce, so here is our equation. So this is our equation. Dou square u by dou y square, dou square u by dou x dou t, dou u by dou x, nonlinear term, dou square u, dou x dou y. So all these partial derivatives. So this equation is basically uxt, uxyt in terms of two-dimensional and space variable. So what we are going to do, we are going to introduce one nonlinear operator on this differential equation. Last equation I have represented by the notation u, but here I have just taken the general v. So this v, which is our differential equation, any nonlinear differential equation, then we are going to introduce one nonlinear operator, which is n, and then equating our entire equation equals to 0. Now this homotopy analysis method, it is actually proposed by the Shenzhen Liu in 1992. Earlier, the optimal control, or I can say their convergence, is described by defining the H curve, and this H curve is generally lies between -1 to 1. But Leo in 1992, he proposed one new technique where, irrespective of the H curve, we move to another approach, that is the zeroth order deformation equation. He introduced this method and not taking the H curve from -1 to 1, but taking it to 0 to 1 to get the more optimum solutions. Now, the solutions, what we are getting it from here, it's somehow you can say the exact solutions. It is near to the exact solution, and we have verified also. So this work, we are doing it, 95% of this work is already completed. Only the physical work is left. Let's start with this approach, this HM approach to solve this Pavlov equation. So nonlinear operator we have introduced on this nonlinear PD, which is defined on y, x, t. And then here it's x and t, but actually it's x, y, and t. Then we introduced the 0th order deformation equation, 1 minus q L, where L is auxiliary linear operator, q is the embedded parameter which comes due to this HA method. Q lies between 0 to 1. Then H is homotopy. What homotopy function says that any function is continuously deformed into the another function. For example, if we are having x and y, two topological space, and we are just introducing f and g, any two functions on this x and y topological space. So f and g are continuously transforming. For example, if we have circle and ellipse, so circle x square by a square plus y square by a square equals to 1, or I can say x square by a square plus y square by b square equals to 1, that is ellipse. So circle is continuously deforming to ellipse. So here homotopy comes into picture. Same way, H here defines our non-zero auxiliary function, which is our homotopy function. Q is the embedded parameter which always lies between 0 to 1. L is our auxiliary linear operator. X, T, Q, again Q is embedded parameter. X, Y, any number of parameters we can use it here. Here this is our initial condition. N is our differential equation, but N on this partial differential equation, which is our nonlinear operator on this partial differential equations. Now, this is our initial guess. This entire homotopy method rely on the initial guess or the initial solution. As we are close to initial guess or initial solution, we are able to obtain the exact solution to any kind of nonlinear PD. Now, generally, we don't have exact solutions to our nonlinear PDs. That's why we are using the numerical methods. But from this method, we can find somehow near to exact solution with very minimum error, or I can say the negligible error. So here, this is our 0th order deformation. When we are going to substitute q equals to 0, we are getting the initial condition. When we are going to substitute q equals to 1, this will get the 0. We are getting the final condition. Now, actually, this is our 0th order deformation. Substituting q0, q1, we are getting initial condition and final condition. Using all these, we are substituting it here. When we substitute here, we need to use the Taylor series to get the solution of our nonlinear PD. When we are going to substitute, so here we have used the Taylor series. This is our nonlinear, the remainder. This is our remainder term. And when we are going to differentiate m times, that the nonlinear deformation function, what we have represented it here, this. When we are going to differentiate this function m times and substitute the values of Taylor series, we will exactly get this function. Now, this is our required function. When we substitute all those values, we are going to introduce this xi-m. Xi-m will get the value of 1 and 0 when I is greater than 1 and I is less than equals to 1. What is this I? This I is actually number of times we are going to differentiate. Because we are going to differentiate m times, so here we will get either 1 or 0 depending upon the derivative we are going to do. So from here, finally we are getting the solution, which is the initial guess and number of times we are going to differentiate. So, we can say this Pavlov equation, as we apply any numerical method to find the solution of this Pavlov equation, if we will just apply this small, what we say, the formulation, we will get the exact solution of this nonlinear PD. So from here, we can get the exact solution, HM solution of our nonlinear PD. Exact solutions are already present here. So then we have shown that the results are comparable. It's in a very good agreement. So this is our exact solution. This is our HM solution. The solution, what we get it from the formulation of HM method. What we are going to use the HM method on our nonlinear PD. So it's approximately showing the same results. So this is the H curve. Earlier it was, we were taking the values from -1 to 1. Now we can say the error is very minimum. Why error is minimum? Because we are using the zeroth order deformation, and due to this zero order deformation, they have introduced this squared residual error. So this square residual error, this T is what T represents. T is actually the time, the small time, what we have used in our PD, because PD, the first thing is, so here is our PD, yeah. So this UXT, space and time function. So here T belongs to 0 to this maximum value. A and B are the constants we have taken, where X, this X belongs to this A and B. X is actually the real number, their domain is X and Y, they belongs to real numbers. And this is our nonlinear differential operator N, and VXT is our final value. When we have substituted the initial guess, then we get this final value. So this is our squared residual error as a result of this HM approach. And when we applied, we can see the error. Okay. Then we can see what kind of results we are getting it. So I'll show it here. So this is the relative error we are getting it. It's like very small error as compared when we have compared the HM solutions with the exact solutions. It's showing very small error, which comes from the square residual error, because generally we don't get it that exact solutions. So this Pavlov equation we have solved using HM method, which is one of the problem of our project. One problem what we have already solved, that is this Kawara equation. Again, it's nonlinear PD, and we can see that we have here, we have third order derivative, partial derivative, and fifth order partial derivative. Third, fifth, and seventh order partial derivative with respect to x. Again, this equation is 1 plus 1 nonlinear PD. This article is already communicated. So then this is Kawara, which is basically useful in the shallow water wave study. So this equation, we have again applied the HM approach. When we applied the HM approach, the same technique, this square residual error is defined by the same formula. We got this H value. What is this H? Actually the auxiliary H parameter, which gives us the error we are supposed to minimize. Now this is up to the fifth order, and we can see as we are increasing, we are getting very small and small error. Then validation of our this HM homotopy analysis method with the exact solutions. So these are the exact solution, and then HM, when we have compared, we have seen that error is very less. Again, this is we have just taken a different time, then a different relative. Again, error is small. These are the comparisons of HM solution and the exact solutions. Now, conclusion here, this HM approach towards any of nonlinear PD, because as we are saying, plasmas, active fluids, reactive fluids, any type of fluid we can model into nonlinear PDs. Nonlinear PDs, and then again subjected to initial conditions and boundary conditions. Right now, two equations, what I have shown, those are without the conditions. But one article which is already accepted, that is Burgers equation. That Burgers equation is with the initial conditions and the boundary conditions. We have applied this HM approach, and then we have seen that we got near to exact solution of that Burgers equation. So the conclusion of this HM approach towards any of the nonlinear PD, it says that semi-analytical solution, or the which is this HM method with the initial condition. Here it's not, but in the Burgers equation it is their initial condition. Using homotopy analysis method, the average squared residual approach is used instead of H curve. Earlier we were using the H curve, but here we are not using the H curve, we are using the average residual that comes from the formulation of this HM method. Two test problems have been considered to use this methodology, which says that the average square residue error approach has been used to find the optimum convergence control parameter, which is the H value, auxiliary parameter, is also known as the optimal convergence control parameter. Then we have shown our results for different values of space and the t at the time. Both here we have shown different values of t and relative error here described. So it's showing very small error. So we can say that HM based solutions, which are the series solutions, we can get the convergent or optimum convergence of our any nonlinear PD with initial condition or without initial condition. So two problems I have shown till now. So these two are without. These are the references. Now, these are the problems. Again, these are without the initial conditions. We have applied this method, and we got pretty much like good solutions to these nonlinear PDs. So then come to, so this is the one paper, this Burgers equation. This is with the initial condition. We have initial conditions of this, what we say is that the Navier-Stokes equation. Navier-Stokes equation, we are defining it. So it's a one, somehow it's a part of that Burgers equation. Burgers equation is a part of the Navier-Stokes equation. So we are going to apply on this method also, and then see what kind of problems we are getting it. But Burgers equations we have already solved using this HM technique, and this is already accepted. Another one is this is communicated Kawara equation. The results have already shown. Now this work is this Pavlov equation, which telling us the commutating flows. It's a part of that hydrodynamic instabilities. This we have solved by using HM method, and now we are going to use the same HM approach on this Fokker-Scan nanofluid flow. So Fokker-Scan nanofluid flow that comes with pressure gradient terms. So here is our continuity equation, momentum and energy. Coupled equation we are having it, subjected to the boundary conditions. So this term is basically our characteristic velocity or pressure gradient, we are using it. Applied magnetic field is there on this pressure gradient, this thing. Then we have shown all these values. Yes. So characteristic velocity is defined by this. This is our magnetic field. Earlier, the same problem, we have published it and we have solved this equation by using the finite difference method and the Runge-Kutta method. For Runge-Kutta method, what we have done, we have just used the similarity transformations. The stream function we have used. Then the stream function, again for the temperature, and psi is the similarity variable. The nonlinear PD, these momentum equation, we have just introduced the one variable, this similarity variable, and then this stream function, we are going to deduce this entire nonlinear PDEs to this ordinary differential equation. This is already solved by using the Runge-Kutta and finite difference scheme. Now we are going to apply this HM method on this. So this when we here we have just used nanofluids, because nu and rho, nanofluid density, nanofluid viscosity. But if we are not going to take the nanofluid, this completes the Navier-Stokes equations. So we are going to apply this HM method on this fluid flow also. Then going to find what kind of results we are getting it, because we already have numerical solutions for this scheme. So this Folger-Scan, as everyone knows, Folger-Scan flow basically defines the accelerated, deaccelerated stagnation flows depending upon the value of m. Whether we are having 0, it gives the Blasius flow. When we are having the value of greater than 0 to 2, we are taking it. So when we are taking it greater than 1, we are getting the accelerated flow, then the reverse flow. So same we are going to apply on this method. So this we are right now working on, and Pavlov is already completed. Yes, thank you.
Okay, thank you, Mittu. Do you have any questions? David?
Could you just say where the Pavlov equation comes
Yeah.
from? What kind of system gives rise to it?
Yes. So this is the Pavlov equation.
Yeah, but what sort of fluid dynamical system leads to the Pavlov equation?
So this is actually dispersionless flows. When we are going, because we have integrable system. So in the integrable system, we got these kind of flows, dispersionless flows.
Do you have a particular sort of wave motion in mind? I mean, is it an asymptotic reduction of long waves of a certain system? Or?
So actually it's the wave, like it represented by the wave function. Like it's wave flow. Hydrodynamic class of function. It's representing by the hydrodynamic class of function. So yes. Physical interpretation we have not done yet. Only the mathematical part, the HM approach we have applied to our this Pavlov equation. But the physical part we are just working on it. Because this thing is an unpublished work, and this is part of our project. So that's why.
Have you ever tried to apply the method to an equation for which it doesn't work very well? And if so, what is the difference between that equation and...
Yeah, because Berger equation, we got problem with the Berger's equation because it comes with the initial conditions. What we have solved, those were without the conditions. No initial or no boundary conditions we have applied to the PDs. But Berger's equation are with the conditions, subjected to the conditions. So there we got problem. Right now we are working on Euler's gas dynamics. Again, it is with the boundary conditions. So there we are getting the problem when we are going to apply on any of the fluid flow with the boundary conditions. Then we get some problem.
Yes, please.
A very naive question. I was wondering if the method works easily when you have a source term on the right-hand side or forcing.
Yes. So right now, what we have worked on, it's, yes, when we don't have any constant term on the right side. Again, with the, for example, if we are taking the Navier-Stokes equation, again we are having that convective terms, diffusive terms, but no constant terms. Gravitation, either we are taking the source or that term, but here till now we have just applied to the constant one. But all other nonlinear terms we have just mentioned it. The same way we are doing it on Navier-Stokes equations.
Okay, then let's thank Mittu again.